there are many kind of angioregenerative. This is one of them. But just to see the complexity of the problem, consider that you inject eight anti-inflammatory agents, and if you, with the same anti-inflammatory agents, you change the distribution, you obtain completely different results for the markers. This is actually for human umbilical muscular. It's a kind of problem that you have to get which is the right combination of a safe box, of a ball. Which is the right combination? Because there are a lot of combinations. Well, I think that maybe regeneratics is doing a good job in guessing in the minimal number of iterations, in the minimal number of experiments, which is the solution that you have. And maybe it could be useful with this small contribution to other companies that want to make less experiments to find the same, to find the goal treatment that they would require. So, to give a particular, very simplistic scenario of what I'm doing, consider, for example, these cytokines, pro-inflammatory, to drive the cell into an initial inflammatory state, and then we are trying to recover the initial state with different anti-inflammatory vectors. Of course, we have some markers to see how things are going on. And the point is that after the initial inflammation, we are able to analyze the complexity of the problem. And after that, maybe you have to make a principal component analysis or other filter algorithm techniques, but eventually you perform machine learning, and in only 2 iterations, you have the 2%, only 2% of the initial inflammation, which is a clinical zero inflammation. So, of course, there are many study limitations. I'm not completely happy with that because we have to test that into we have to test it in vivo. This is just in silico. So it's fine, but we need experimental validation always. And the good point is that we have enough data. We were able to do a deep learning to predict with 0 iterations the results. And in the X layer, we have the number of tests, so 200 tests. And basically the results overlap in reality with the prediction. So I think it's been a good job made by Lucas, which is here. I'm very happy with my team, by the way. And it's great, but we are very lucky to have here Dr. Pichardo, also made a postdoc with David Sinclair. Thank you very much.
And we decided to partner with regeneratics and the process team because we are interested in modeling not only the secretomics, which we are very interested in, which is a tool that we want to use in order to improve and extend health span in people.
This is something that connects with the last part. I think it's very interesting because we take into account in our models that something that we knew intuitively, that is the cells are able to adapt and to react. And how is that possible? Because very probably there were a kind of machine learning inside the cell, intracellular. And those evidences have been recently published. This is in September, 1 month ago. 1 month ago, they were able to store 100 bits of information and perform machine learning with the molecules dying intracellular. So this is machine learning proteomics driven, and it has been published in Nature and Nature Biomedical level. So intracoronary and microvasculature around the intracoronary. We failed, and we wonder why we failed. And maybe when we attended to the traditional convolution model that is in the normal artificial intelligence of as industrial secret more things, but we find out that probably it's because there are no true convolution in time. The cells make that kind of artificial intelligence. It's not artificial, it's bio-IA. And they are able to do that, but they interact in the real time. So molecules are not going to flip in each iteration. Numerically, when you do an iteration, the numbers flip. There is a glitch in numbers, but the cells don't do that. They remember everything, and mathematically, that's a convolution, a true convolution network. So we made a new kind of true convolution neural network that I call it truco, because truco in Spanish means trick. So truco, and with this new model, we were finally able to control inflammation at the cellnet. Not only cell therapy, but cellnet therapy. Now, okay, that was the thing. So the point is that, oh, it's a pity. But this is a real-time conversation of the cells. It's a pity because I should have expanded. Oh, 1 minute. Okay. And then we have a stabilization of the signaling pathways and finally the markers. And this is the result. We were able to control the inflammation. The red is bad, green is not anti-inflammation, but at least control the inflammation in the myocardium. Thank you very much for your attention. Feliz año en the Kaishu. Y gracias, muchísimas gracias.